Okay, gentlemen. So this week we will be beginning the unit on stoichiometry, which is what I had told you for a lot of people is the hardest unit in chemistry. So this is a little less than ideal working online and not in person on this, but we'll get through it. So stoichiometry combines the last two tests, basically. It combines doing molar conversions with balancing equations and also predicting products and reaction types. So the last kind of three things we've been doing all get combined into stoichiometry. And stoichiometry is a really important branch of chemistry. It's basically an accounting of how much goes into and comes out of chemical reactions. We need to know how much we are going to get out of a certain chemical reaction, especially if we want to make a certain amount of product, or how much ingredients, how many reactants we have to put in to get the right amount of product. Another reason we might need to know how much goes into or goes out of chemical reactions, let's say we have an acid we want to neutralize. We need to know how much base to put in with that acid to neutralize it exactly. We aren't just going to randomly guess. So stoichiometry uses balanced chemical equations to determine how much stuff is coming into and going out of chemical reactions. So the first thing with stoichiometry, again, is that it's a balanced chemical equation. So I have an example here. Nitrogen plus hydrogen gives us ammonia. We've seen this a bunch of times, the Haber process for producing ammonia. And the first thing you have to do before you do anything else when looking at a stoichiometry problem is balance the equation. So I'm going to quickly balance it. I'll start with balancing the nitrogens. There's 2 on the product side, so I'll put a 2 over here, or 2 on the reactant side, excuse me. So I'll put a 2 over here by NH3 to make there be 2. Now there's 6 hydrogens here, so a 3 here. We have 6 hydrogens and 2 nitrogens on each side. That's a balanced chemical equation. And what this tells us is really the key to stoichiometry. This balanced chemical equation actually tells us how many moles of each thing react. In other words, we could rewrite this out in words as 1 mole of N2 plus 3 moles of hydrogen, H2, gives us 2 moles of ammonia gas. And here's why that's important. From moles, we can get to things like grams, or liters, or even number of particles. We know how to do those conversions, or at least we did several weeks ago. We may have to brush up again. But if this tells us how many moles of each thing there are, it can also tell us how many grams. So if we're going with 1 mole of N2, and I'm going to be abbreviating a little more, rounding a little more than usual just for the sake of clarity. That's 28 grams of N2, plus 3 moles of H2, that's 6 grams of H2. And that's going to give us 2 moles of NH3. NH3, 1 nitrogen, which is 14, 3 hydrogens, which are approximately 1. So that's 17 for ammonia. So 2 of those would be 34 grams NH3. So we can actually tell how many grams go into and come out of a certain chemical equation. And there's something very important happening here. Those of you who are paying attention and being clever might have already figured out we have 34 grams on the reactant side. And obviously 34 grams on the product side. We cannot create or destroy matter. I've said this many times in class. We're kind of a puny little species, and all we can do is move matter around a little bit, except for nuclear reactions, which occasionally destroy the equivalent of a neutron. We don't create or destroy matter. All we do is push it around. So however many grams you start with, you need to end up with that many grams. There's no way around it. So if I had 28 grams of nitrogen and 6 grams of hydrogen, they would make 34 grams of ammonia. The mass would be the same because the atoms are the same. Again, this is a balanced equation. We have the exact same number of nitrogens and hydrogens on each side. The rearranging of them doesn't change their mass, doesn't change their weight. So that is what we call conservation of mass. And it is the key to balancing equations and one of the keys to stoichiometry. So again, we cannot create or destroy matter. And that is true of any balanced equation we have and any of the stoichiometry we'll be doing. nothing will be created or destroyed. You'll always have the same amount that you ended up with as you started with. Okay, so let's look at an actual stoichiometry equation, the basic type that you would see and we'll see on your worksheets and quiz. If I have 25 grams of hydrogen gas, H2, how much ammonia can I make? We're assuming we have all the nitrogen we need. And for this week, we will only be looking at one of the reactants or one of the products. And we won't be worrying about the amounts of the other one. So I have 25 grams of hydrogen. Assuming I have all the nitrogen in the world, how much ammonia can I make? So this is your basic stoichiometry problem. This is a real-life problem. When we measure things in the lab, we tend to measure them in grams, or for gases, sometimes liters. We aren't going to measure them by moles or by individual atoms. So if I have 25 grams of hydrogen, which is an amount I can measure in the lab, how much NH3 can I make? That's a real and practical problem. So I've given you the balanced equation from the previous page. So it's still 1 nitrogen plus 3 hydrogens gives us 2 NH3s. The steps to any stoichiometry problem are pretty simple. And I will give you guys online a step-by-step guide. It's just called How to Do Stoichiometry Problems. But the first step after balancing the equations, once you've got a balanced equation, step 1 is to convert the given quantity to moles. So whatever your given quantity is, in this case, that given quantity was 25 grams of hydrogen gas. And by the way, it is important to keep the H2 with that 25 grams. You want to be able to keep your products and reactants separate, your different chemical properties, because now in these conversions, we will actually have more than one chemical. So I'm going to keep writing out my chemical formulas, and I strongly suggest you will too. So this is going to be a series of conversions. So the first step in the conversion is 25 grams hydrogen gas over 1, and hydrogen is 1.01. I'm sorry, that's wrong. Hydrogen gas is 2.02 grams per mole. So we'll put that on the bottom because we want to get rid of grams and get to moles. And I will put H2 with both of these, just keep it straight that I'm still talking about my hydrogen. So that's our conversion. And I'm not actually going to set up do the math yet, because I'm going to set up my entire set of conversions before I do anything else. So step 2 then is to convert from moles of the given chemical and this is going to sound a little weird, to moles of the chemical that is asked for. So we're given a number of moles of hydrogen, and we're asked about ammonia. So I'm going to convert from moles of hydrogen to moles of ammonia. But how do you convert from moles of one chemical to moles of another chemical? And this is the first time we will be doing this, converting from one chemical to a different chemical. And the key to this is the balanced equation. I know that for every 3 moles of H2, I'm going to get 2 moles of NH3. The reason I know that is from the balanced equation. So you're going to use the coefficients from the balanced equation. So in this case, it's important to set it up so your units cross out. So we want to get rid of moles of H2, so that goes on the bottom to cross out. Moles of NH3 on top. And I literally just looked at the balanced equation and took those 2 coefficients. NH3 has a 2 in front of it, 2 in front of NH3. H2 has a 3 in front of it, 3 in front of H2. The last step, and this does actually convert us to moles of NH3. The last step, step 3, is to convert from moles of the asked for chemical to whatever quantity is requested. In this case, and all that means is we got moles of NH3 here. What's it asking for? Is it asking for moles? No, then we have to convert. What's it asking for? Well, I didn't specify, but I'm going to go with grams. So let's change that question up top. Since it gave me grams, let's change that question to be specific. And since it gave me grams, I'll just ask it for in grams. We will convert from moles of ammonia to grams of ammonia. So the conversion factor here is just the molar mass of ammonia. So 1 ammonia is 17.04 grams. And that's it. That's all our conversion factor. And if you look, you cross out grams of H2, which is what you started with. Then you can cross out moles of H2. Then you can cross out moles of ammonia. And what you end up with is grams of ammonia, which is what the question asks about. So that is how you set up the conversion. Once you do the conversion, or at least once you have the conversion set up, now it's just a matter of punching buttons on your calculator. This would be 25 divided by 2.02 times 2 divided by 3 times 17. You can type in the times and divided by 1 if you want. I'm not going to, but you certainly. So for any of you interested in or who have been following along and doing the math, if you do all that math, you get 140.6 grams of ammonia, which, because you only have 2 sig figs to start with in that 25 grams over here, I limited my answer, rounded my answer to 2 sig figs. I won't be picky about that, but that is the proper way to do it. So rounding, you get 140 grams of ammonia. So with 25 grams of hydrogen and all the nitrogen you could possibly ever want, you can make 140.6 grams of ammonia, or 140 rounded to sig fig. Okay, so here we have another basic type of stoichiometry problem. Using methane plus oxygen. I've already balanced the equation. We can cover balancing a little bit again, but you guys should be fairly comfortable with balancing. So this is the combustion of a hydrocarbon. Methane plus oxygen gives you H2O and CO2, water and CO2, which is what combustion of any hydrocarbon will give you. How many grams of CO2 comes from burning 225 grams of methane? Well, this is actually a fairly common type of chemical equation that people work with. If you ever heard the term carbon footprint, like your carbon footprint, they actually mean how much CO2, the energy you use, is made, well, how much CO2 is made for the energy you use. So you get energy, electricity, by burning coal, which is primarily a hydrocarbon, or by burning natural gas for heat, which is methane, or propane, or some other way. And when you burn that to produce energy, which is turned into electricity or heat or whatever you're using, it makes CO2 and H2O. So when we talk about carbon footprint, we're actually talking about how much CO2 you're making. So this is the type of equation that is actually used to figure that out. So I'm going to set it up, and I'll come back, and we'll look at how. Okay, so we've got the conversion set up. We start with 225 grams of methane. We just put that over 1. That's what we're given. And we're going to convert that to moles. The first step in all of these problems, all of these stoichiometry problems, is to convert into moles. Because moles is the only thing that allows you to go from one chemical to a different chemical, which is generally what we want to do in stoichiometry. We want to figure out how much of a different chemical we are making, or we need to make, or we need to react with. So generally, you're going to convert to moles, unless you start with moles. So Molar mass of methane, CH4, is 16.05. 12.01 plus 1.01 plus 1.01 plus 1.01 plus 1.01 gives us the 16.05 grams per mole. And the next step, after we convert to moles, is to convert from moles of one chemical, of the chemical you're given, to moles of the chemical you're asked about. In this case, we're given methane and asked about CO2. So I'm going to put moles of methane on the bottom. That's what we want to get rid of. That's what we want to cross off. And moles of CO2 on top. And the conversion factor here is one of the easiest things you do in chemistry. Once you have the balanced equation, all you do is look at these two chemicals and you grab the coefficients in front of them. So in front of CO2, there's nothing, which is the equivalent of 1. And in front of CH4, again, there's nothing, which is the equivalent of 1. Putting nothing in front by default means 1. So for every 1 mole of methane we burn, we make 1 mole of CO2. That's what that conversion factor means. And that's all there is to that. The last step, because this is asking how many grams, is we're going to convert from moles of CO2 to grams of CO2, which is just another molar conversion. 1 mole CO2 on the bottom, stuff we want to get rid of, grams of CO2 on top, and CO2 is 44.01 grams per mole. Again, that's just 1 carbon, 12.01 plus 2 oxygens. So really, all this is mole conversions plus 1 additional step. And that additional step is this middle part where you convert from one chemical to another chemical. Other than that, it's just grams to moles going in, and then moles to grams going out for this equation. Now, it doesn't have to be grams to moles. It could be liters to moles or particles to moles. But you know all those conversions, and they will all work the same way. The only different step is this middle step where you convert from one chemical to a different chemical, and you do that with the balanced equation. So you need to make sure your equation is balanced. Okay, so again, I've done the math, and if you do all the math, 225 divided by 16.05 times 44, and again, I'm just ignoring the ones, multiplying, dividing, you get 616.96 grams of CO2. Because I started with 3 sig figs, I'm going to convert or round to 3 sig figs and call that 617 grams of CO2. So my answer will be 617 grams of carbon dioxide. So when you burn 225 grams of methane, you get 617 grams of CO2, plus some amount of water and also some light and some heat. You're particularly interested in the heat energy or the energy that you're getting out of there. But you also, as a byproduct, make this CO2. And that's, again, the basic idea behind the carbon footprint. When we burn hydrocarbons to get energy, we make CO2, and that CO2 is a greenhouse gas and affects the atmosphere, and that's why they're particularly worried about that product, and that's why they call it a carbon footprint, because you're kind of following the carbon from one side of the equation to the other. So this is stoichiometry, and I will come back on tomorrow with another quick video of me doing a couple problems, but again, it's really just conversions with one additional thing. This conversion from moles of one chemical to moles of a different chemical. Other than that, it's just molar conversions that you have done. Yes, you have to start with a balanced equation, so make sure you balance all the equations before you start. And yes, eventually we'll get to the point where I just give you like CH4 and O2, and you have to know its combustion and predict the products, and then balance it, and then you would do all the stoichiometry. But for now, just make sure you start with a balanced equation and do the conversions. Conversions aren't hard. There's a lot of steps, but they aren't hard. Also, remember, there's a how-to step-by-step guide that I will put up with the post for this video, and there is a worksheet as well. So that and the due date information and the Google Form link where you will turn it in will all be up on PowerSchool and Google Classroom. Hope you gentlemen have a good day. Again, this week is stoichiometry. Next week is stoichiometry. It's what we'll be doing till Easter break. There's a lot of steps. It's the hardest thing for a lot of kids, but if you can keep your steps straight, none of these steps individually are hard. This is how a lot of chemistry goes. A lot of meticulousness, a lot of steps you have to keep straight, but as long as you put them in order, at the end of the day, it's just multiplication and division. Have a good day. Enjoy your start to the week. Hope your weekend went well.